So I'm going to be your presenter today, and within an hour, I'll give you a sense of what you can do with SIMULIA nonlinear analysis, which is not as scary as some people might think. We'll do a live demo, and you'll get a good understanding of what's going on. So the webcast topics, as you see, I'll give you a quick overview of CATIA SIMULIA analysis portfolio. And then we'll go through a demo. Essentially, it's a simple model, and we'll see how can you simulate inserting a clip into a steel panel. We'll finish with a summary and Q&A session. So if you have any questions, just write down and share with me and the marketing hub, and I'll respond to those questions during the Q&A session. What you're going to do is work with SIMULIA analysis. And this slide presents you an overview of the CATIA SIMULIA analysis portfolio. I'm sure some of you have already worked with CATIA GPS, which is a linear static analysis and dynamic analysis in CATIA. The basic idea of this workbench is that it provides basic linear analysis for CATIA users. And a few years ago, about 5 to 7 years, Dassault acquired a company called Abacus, and this is the industry standard for nonlinear and advanced finite element simulation. So we had a bit of a gap in here because the software intended to be used by design engineers and CAD engineers was only able to provide linear solutions, and Abacus is a very complex tool which is, intended to be used by CAE analysts. So what this came about a few years ago, a couple of years ago, they created an ANL and ATH workbenches in CATIA. So this one provides you access to Abacus capabilities, Abacus solver, and on the upside, it's fairly easy to use, and it is embedded into CATIA, and you can pretty much run static simulation, thermal simulation, and the intent is that this workbench is to be used by CATIA engineers. Okay, so as I was saying, a quick idea about what is linear versus nonlinear analysis. In the linear analysis, everything considered to be a kind of a spring. In other words, the structural stiffness of your model remains constant during the loading process. So as you see on the right side, a simple spring, and the relationship between the force and the displacement of the spring is linear. With a nonlinear analysis, the case, the stiffness of your model is actually changing during the loading process. There could be different reasons. The first one is the material nonlinearity, such as plasticity. And for instance, if you look at the typical stress-strain curve, once the material starts yielding, it becomes softer with the work hardening and so on and so forth. So the response becomes nonlinear. Another type of nonlinearity is the geometric nonlinearity. Simple example presented on this slide, you have actually it's a rubber button, and if you push through it, it experiences so-called snap-through behavior. In other words, initially the stiffness changes, the stiffness increases, and after a certain amount of displacement, it actually snaps through and the stiffness decreases. That's an example of geometrical nonlinearity. And lastly, you may have a model with a boundary nonlinearity as a contact. Contact between different parts, and in this slide you see an example of what is called self-contact, where the surfaces within the same part start or get into contact during the deformation process. So what I'm going to be presenting, I'll be running a simple analysis problem. And we'll be taking a look at how would you simulate with the ANL workbench insertion of a plastic snap fit clip into a steel model. The task for this simple demo is we want to estimate the insertion force. We also want to determine maximum stress on the clip snaps. And we also want to determine possible permanent deformation in the snaps after insertion. Okay, so why this model, why this problem is nonlinear? Well, actually, despite its kind of simplicity, it involves all three kinds of nonlinearity. So first of all, the stress in the clip may actually exceed material yield point. And so therefore, there might be some plastic deformation at the clips, and we need to model that. Secondly, it's a sliding contact with large displacement. As you see, through the steps of the insertion process, initially the clip starts touching the upper edges of the hole, and once it goes through, it's a large deformation sliding contact between the parts. So can we possibly use GPS to simulate this kind of a problem? Certainly not. We have to use ANL. Okay. So I'm going to be switching now to CATIA, and I'll be writing CATIA V5 R2014. The interface is pretty much the same, the workbench in earlier releases, and actually this ANL product is available starting from R19 if you have one. Okay, so I'm going to hit escape. Hopefully I'm not going too fast, and you can follow what I'm saying, but because the time is of essence, I'm kind of trying to squeeze as much as I can into my presentation. Okay. So now we've seen a CATIA window, and that's the model we'll be analyzing. For efficiency, as you see, we're going to be considering 1/4 of the model. The gray part is cut out of the steel panel, and the brown part is actually 1/4 of this insertion clip. So the first step is to apply material, and the steel panel is made of steel. So we're going to apply material. We are in the assembly workbench. So I'm going to click Apply Material, and I'm going to go looking for steel. I'll just drag and drop. So I'm going to drop it onto the whole part. There you go. Okay, so I see there's a steel applied. Now I'm going to apply a different material to the clip model. So I'm going to hit clip, and that's going to be a general plastic, general ABS plastic. So I'll use, let's say, this one. Again, drag and drop on the clip. Okay. So let's take a look at the material properties. I'm going to double click on the steel. Okay, and if you go into analysis, you see there is Young's model, Poisson ratio, density, etc. All the properties needed for a linear simulation. If you go into the nonlinear and thermal, this one actually provides some additional capabilities. So it turns out you can also define plasticity, hyperelasticity, density, thermal conductivity, and so on and so forth. Now, do I need to specify any nonlinear properties for the steel panel? Actually, no. I should be good with linear because during the insertion of this clip, the likelihood of any plastic deformation is next to being non-existent. So I'm going to cancel it, but it's not so with the plastic. So I'm going to in the plastic material, okay? So now I'm going to switch into nonlinear and thermal properties. Okay, and basically in this simulation, the expectation is that there will be some area of plastic deformation in the clip. So we're going to be modeling it using Elasto-Plastic material. So we're going to need to check two boxes, elasticity, and here you have Young's modulus and Poisson ratio. It could be made temperature dependent if needed. And also I'm going to check plasticity. So plasticity requires entering stress and plastic strain. And I can also make it temperature dependent if needed. Now, whenever you deal with plasticity, etc., you actually need to do some prepping. So I'm going to go back to my slides, okay, and we'll take a look at this one. Okay, so essentially, if you do tensile testing of specimen of a material, you obtain a stress strain curve in terms of what is called engineering or conventional stress versus engineering or conventional strain. So Abacus, however, requires the data to be entered as true stress and true plastic strain. The formula is, however, very simple. So to get, let's say, true stress values, that's the formula to be used. So the S is engineering stress and E is engineering strain. And true strain, that's another formula. And also we need to calculate true plastic strain. So the easiest it is done using a spreadsheet. So for instance, I'll show you an example of a spreadsheet. So I'm going to go in here. Okay, so as you see, I had an experimental data, test data, which is the green one, and I simply put it into a spreadsheet, and I put a formula. For instance, if I click on this cell, there is a formula. If I put on this one, and so on. So as you see, there are all calculations done in here. So, but essentially what I want for my is plastic strain, which is this column, and also modulus of elasticity, and also Poisson ratio. Okay, so I'm going to be entering this data, and it's done pretty straightforward. Okay, so elasticity, Young's modulus, that was the value. Okay, that's 2668, 68 megapascal, and Poisson ratio, that was 0.4. Okay, so now we're going to switch to plasticity, and we describe plasticity. Let me expand it a tiny bit. Okay, so the first row is at the stress 45.8, there was 0 plastic strain. Fair enough. Okay, let me expand it. So there's an option, add a row. So, and then I'll pretty much go through the other steps. So at the stress 53.4, the value of the plastic strain was 0.015. Add another row. So that was 61.1. Again, all this data is in the Excel spreadsheet that I had, and actually you can import data from file, which simplifies. But I'm doing it here manually because it's just a demo anyway. So there's going to be 0.47, and I'll add another row. So let's say that's going to be 78 megapascal, and the plastic strain 153. Okay. So hit OK, and we are done with the materials. The next step now, we need to switch to the analysis workbench. So I'm going to go Start, Analysis Simulation, and this is Nonlinear Structural Analysis Workbench. Okay. So as you see, the environment changes, all the icons change, etc., etc. Everything is now different. So what's the first step? Okay. The first step, we need to mesh the model. And the meshing process is very much the same as in GPS. By default, as you see, CATIA created 2 meshes. One mesh is for the hole, and another is for the clip. Okay, so I'm going to double-click on the clip mesh. So there's a size parameter and the sag parameter, and I'll just uncheck for simplicity the absolute sag, which controls the accuracy along the curved surfaces, and I'll use the value 0.5 millimeter. Okay, so that's a fairly small mesh, as you see. And I'll also double-click on the hole. Again, I'll uncheck the absolute sag value. I'm not concerned with that yet. And I'll put a value of 1 millimeter. Okay, now what I also want to do, we can actually visualize the mesh real quick, so I'm going to right-click Mesh Visualization. So it actually meshes the model, okay? Because there will be contact between the clip, which has a much finer mesh, and the hole, which has a coarser mesh. What I want to do is to get a good accuracy of the contact analysis to make meshes roughly the same size on the contacting surfaces. So what I'm going to do is apply a local mesh control over this surface. Okay, I'm going to delete the image, and I'll deactivate. I'll hide and show. Actually, right-click, hide and show. And I'm going to change the setting, the local setting for that area. So I'll do local size, add. Click on the surface, and I'll use the same value as I did for the clip, which is 0.5 millimeter element size. Okay, so unhide, and I'll do mesh visualization. Okay, so as you see on the curved surface, on the whole surface in the cylinder, the mesh density is now the same as on the clip surface. Okay, fair enough. What's next? Well, here's what I'm thinking. Again, for efficiency, here's what you might want to consider. Let me clean up the model, okay, and I'll hide nodes and elements. Okay, so the steel panel is made of steel, which has Young's modulus by a couple of orders of magnitude greater than the plastic. So what I can do for efficiency is actually make this part as a rigid body. And I'll use what is called the rigid body constraint. I didn't have to do it, but for efficiency, as I said, the rigid body constraint simplifies computations and the analysis just runs faster. So I'm going to use rigid body constraint, support, let's select this body, and I need to select the handler. The handler essentially, whenever I apply a load or a boundary condition to a rigid body, I'm effectively applying it to the handler. And all I'll do is just select this vertex. Okay, that's fair enough. That's rigid body constraint. And also I'll create another rigid body, but now using an option rigid virtual part. Essentially, in this simulation, what I'll be doing is pushing the surface of the clip in the downward direction. And because I need to extract reaction force, I'll be pushing this point. It's a datum point or a three-dimensional point in CATIA, and I need to attach this point to the surface somehow. So what I'm going to do is to use rigid virtual part to accomplish that task. Now there are several options. You see there's a smooth virtual part, rigid virtual part, and some options with the spring. I'll just use the rigid virtual part. So it's going to be attached to the top surface, and as a handler, that's the point that I will be pushing in a downward direction. I'm going to select this one. Okay, pretty much done. So now if we visualize the mesh, we actually see some additional stuff in here. Going to run mesh visualization, okay, and unhide the mesh. Okay, you may notice those light blue lines. These are actually rigid links that connect the handler with the surface, and so on. Clean up the view and hide the mesh for now. Okay, so now we're going to need to create what is called a simulation history. If we take a look at the what's created in the model, you see there's a simulation history, and right now there is only one static step, which is static step .1. So what is the simulation history? The fundamental concept of abacus analysis is that everything is considered to be happening in time domain. So in other words, your ANL analysis case represents the history of a model exposure to all kinds of time-varying loads, and this is what is called simulation history. Like on this slide, as you see, the simulation history consists of initialization steps and actually 3 static steps. So generally, an analysis step represents a logical state in a simulation, which means loads, constraints, and other environmental effects may apply during one simulation phase, but during another phase. Different analysis procedures could be used, for instance, static, frequency, during different simulation phases. And the step succession rule to be remembered, the end condition of any given analysis step are considered to be the initial conditions for the next step. So how many steps do we want to design for this one? Well, here's what I'm logically thinking about this case. What happens during different insertion phases is that friction coefficient changes. Like during step 1, as you see, the surface actually rubs against the sharp edge, and the friction coefficient is about 0.3. Now, when the clip goes through this and slides along the smooth surface, the friction coefficient becomes 0.1. And lastly, the clip again rubs against a sharp corner, sharp edge, and the friction coefficient is 0.3. So keeping that in mind, actually I'll be designing my simulation history as 3 steps. And I'm going to start with just step 1, which is insertion of the clip up to that point. Okay, so up to the position where the clip start sliding against the smooth surfaces. So let me go back, and that's going to be my static step 1. And now I need to set up boundary condition and so on and so forth. Okay. So we need to change some settings. If you double click on the static step 1, see the settings for nonlinear geometry, off or on. I'll do it on because it includes geometrical nonlinearity. Time duration, step time. It's actually not a physical quantity, but 1 second works just fine for me. Initial increment size. So essentially, for nonlinear simulation, the rule of thumb is to set about 5% of the total steps. So if the step time is 1 second, 5% makes it 0.05. Okay, so now applying loads and restraints, and I got to apply fix the steel panel, which is I'm going to look for the clamp, and the clamp is right there. Okay, and I'm going to select the vertex which I used for the handler for the rigid part. Okay, also apply symmetry constraint. Okay, so I'm going to do symmetry, which is general. So on this surface and on, yeah, this one is not needed because it's rigid. And direction is along y direction. So that's a symmetry constraint on this side. Another symmetry constraint now on that side. Clicking that surface, and that's going to be x direction. Okay, now loading. How do I want to load it? What I'm going to do is actually enforce or force this clip into the hole. So I'm going to be using displacement or enforced displacement control. Okay. So I'm going to click that. And I'll select the handler point for the rigid virtual part. Okay, and this one will be forced into U3 direction. Okay, so the U3, which is the direction, it is vertical, and I'll be enforcing it by about 1.8 millimeter, which roughly the amount of displacement until the clip is fully inserted into the hole. So we may notice that actually it creates a whole bunch of stuff in here, boundary conditions. So there is a clamp, there is a displacement 1, displacement 2, and displacement 3. So it's all there. Now, I also need to take care of the contact pair because I need to describe how or which surfaces will be in contact when this clip is being inserted. Okay, so I need to create what is called a general analysis connection. And the contact will be between the cylindrical surface of the hole. And for the second component, I need to select all surfaces which will be getting into contact with the hole. So that's one surface, that's another surface, that's another surface. You see, these are all the surfaces which will be in contact with the hole during the full insertion process. And that's going to be the last one. And now I need to create mechanical connection behavior. So by default, the contact is assumed to be frictionless. If I want to introduce some friction, I need to create what is called mechanical connection behavior. So let's click on that. Description, I can add description, tangential behavior, penalty, which is friction. As you see, there are some other options, frictionless, rough, user-defined, and so on. The basic one is a penalty. And all I need to do is define friction coefficient. So for the first step, that was 0.3. And that's pretty much it. And hit OK. Now, the contact is not yet fully defined because I need to create another entity, which is this one. It's called contact pair. Okay. So I'm going to select contact pair. Support. This is my general analysis connection. As you see, the process is actually very similar to how you do it in GPS analysis, okay? So the sliding formulation is a small sliding, a finite sliding. Well, that's a finite sliding or large sliding. I need to keep it that way, okay? And also, I need to take care of what is called master and slave surfaces. As you see, one surface is shown in red and another in green. So the red is the so-called master surface, and the green is so-called slave surface. The adequacy technology ensures that the slave surface does not penetrate into the master surface and vice versa. So looking at this model, I'm thinking, okay, actually I need to make sure that this edge, the sharp edge of the hole, doesn't penetrate into the clip material. So therefore, I'm going to make this as a slave. Okay, and I'll do it by simply swapping the surfaces. Okay, so the green is now the slave, and it will not be able to penetrate into the red surfaces. And that's pretty much it. All set. So I think my model is fully set up. The only other step is taking care of output requests. Okay, so as you see, there's a field output request, history output request, and a data output request. So let's take up another slide. We'll talk a tiny bit about output requests. So there are three types. Field output request, this is used to display results in the form of color plots at specific time instances. This is just a typical color fringe plot. And a default field output request is automatically created. History output request is used for graphing results at a specific point versus time. And lastly, data output request used for exporting results to a text file. Now, do I need other requests than the default field output request? Well, actually, yes, because what I want to monitor is the insertion force for this clip. Okay, so I'm going to create what is called a history output request. You see, there is a field output request, and that's a history output request. Okay, that's not going to be for the whole model. And all I want to do is select just the point, which I'm driving through the hole. Okay. Pre-select defaults. I don't need pre-select defaults. I actually need to select what I want to have, and this is reaction force in Z direction. Okay. So I'm going to scroll down looking for reaction forces. There are strains, plastic strain components, and all that goes in elastic. Logarithmic, but I'm looking for reaction forces, translations, forces, and moments. Okay, so reaction forces, and because I need this Z direction vertical, I'll just check RF3. Okay, so now my model is ready, and I can create what is called a job. Okay, so if I double-click, you see right now it says analysis 1.1. If I double click on it, there are some settings, whether I want to run model consistency check, some general settings, memory, parallelization, etc., etc. For simplicity, I'll just keep all the defaults. Okay. Submission. So actually, I'm going to need to do some settings. Hold on a second, because it outputs a whole bunch of different files. I'm going to go into analysis and simulation, and nonlinear and thermal. As you see, I'll just create a folder on the desktop. You see there's a desktop TMP. That's what I'm going to use for the subroutine and so on. I'm going to call it TMP, temporary folder. Going to go back into CATIA, double click on the analysis. So these are all the settings, trash directory, fair enough, subroutine directory. I'll just go into the desktop, and I'll pick my temporary folder. And same here, desktop, and it's a temporary folder. And lastly, I'll use it also as a scratch directory. You could use some defaults, as I said, using settings, which I didn't select. Click OK, and it takes it just fine. Okay, so the model is ready now for submission. And to start actually a job, you need to use what is called a job manager. Okay, see there's a job manager. So you can actually have several jobs, so several cases, etc., etc., and we can submit we can monitor and so on. Now, the way it works actually, when you click submit, what happens is CATIA actually outputs a neutral file, which is Abacus INT file. And then on the background, actually Abacus solver starts and reads the file and then produces results, solve and produces results. I don't want to run this model. It takes about 10 to 12 minutes. We don't have that much time, unfortunately. But in general, as I was saying, you click submit and actually start the job, and we can click at this point monitor and actually observe what's happening. So if we have any convergence issues, if we have any other issues in the model, we would know at this point. So in this model, as I said, I don't want to solve it. What I'm going to do is simply attach the result that I solved before, pre-created before. To do that, I'll just create a new analysis file, analysis document. Okay, and there is an option to actually attach a result database. So it says import result database. And I'll use, as you see, there's an ODB, which is output, Abacus output file for step 1, which is exactly what I have right now in the model. Okay, so it shows me the mesh. Let's run a couple of animations. So I'm going to use this. So that's the final position. As you see, exactly as desired, the clip just starts sliding along the smooth surface of the hole, and we can do an animation. It goes back and forth. And that's a real-time animation. This is not something like a linear animation in a linear analysis. This is actually how the clip is getting inserted. Okay, so let me check a couple other things. I want to know if there's any plastic deformation in the model. Okay, so I'm going to right-click, generate result image, and what I want to have is equivalent plastic strain. Okay, that's at 0 step, and I'm going to go to the last one. Okay, and as you see, it turns out, yes, as anticipated, actually there was some plastic permanent deformation and plastic trace occurring in those two areas. So at this point, I would make some decision: is it acceptable, is it not, and I can actually get the amount of permanent deformation. But the other thing I was interested in this simulation is getting the reaction force or insertion force. To do that, there is a tool which is called, as you see, plot history data. And this one actually gets access to my history request. Okay, the reaction force in vertical direction. I need to select static step. Click plot. It actually outputs data into Excel spreadsheet. And I may notice that actually initially the insertion force increases with the amount of displacement. Then it reaches the maximum, and then it starts decreasing. It kind of makes sense because initially the angle, how the surface rubs against the sharp edge in this area is pretty sharp. But then once it starts sliding along the smooth area, the reaction decreases. And if I want to get a value, I can click on the second tab, which is history output request. So this is the max was about 4.26 newtons, 1/4 of a model, so it's roughly 17 newtons. That was the maximum insertion force during this step 1. Okay, so far so good. As you see, we were able to successfully simulate the first step in the simulation, which was insertion of the clip up to that point. So let me pop up the plot again. Okay, so essentially we only simulated until the position in which the clip starts rubbing against the smooth surfaces. We want to add some other steps to actually make the full insertion of the clip. Okay, so I'm going to detach the base, and I need to create some other static steps. Okay, so I'm going to click. That would be my static step 2. Again, I'll use the same default, which is 1 second total time, initial increment size, which is 0.05 seconds, which is 5%. Hit OK. Now, if we take a closer look, as you see, the static step 2 now becomes active. Static step 1 is step number 1, and automatically all the output requests and boundary conditions are propagated into the second one. Okay, see there's a field output request, which is exactly the same as here, history output request. Okay, it also takes in all my connections, but as you recall, the frequency, the friction ratio for this step is actually 0.1, it's not 0.3, so I gotta change it. So therefore, I need to create another mechanical connection behavior. But now instead of 0.3, I'm gonna use friction coefficient 0.1. Okay, and now I need to use this new connection behavior in the contact pair. So double click, connection behavior, and I'm going to select, you see, nonlinear thermal properties, mechanical connection behavior 2. Okay, so in the first step, that was mechanical connection behavior 1, which friction coefficient 0.3, and this one is connection behavior 2, which friction coefficient 0.1. Okay, so that's why I had to do it using different steps, static steps. And lastly, I also need to change boundary condition. So displacement 3 was controlling the enforced displacement in vertical direction. Gonna double click. So you see initially it only went up to 1.8 millimeters. The next step is actually another about 1 millimeter. Let me find the value real quick. And if I'm not mistaken, hold on a second. Yeah, that was 6.25 millimeters. It's okay. And at the same time, I want to create another step. So the last step, if you recall, which the insertion step, let me bring this slide, okay? So you see the clip starts again rubbing against the sharp edge. So the friction coefficient goes back to 0.3. So I'm going to create another step. That's static step 3, same parameter for nonlinear behavior, and so on. And I need to make some changes. You see the contact pair 1 still uses connection behavior 2, but I want to go back to the first one, which is friction coefficient 0.3. Is okay? And I also need to change the amount of insertion. Okay, and that was let me find it, 6.7 millimeters. So that was boundary condition 3. That's 6.7 millimeters. Okay. Now, I also need to do something else, because once I fully insert the clip, there will be another contact occurring, which is between this surface and the top of the steel plate. So I'm going to create another general analysis connection. I'm going to select that. Second component, select that. Okay, and I'll create another contact pair, which is now using that one. If I don't select any connection behavior, it will be assumed frictionless. Now, do I need to swap a master and slave? Well, what I want to do is to make sure the red surface doesn't penetrate into the green one. So actually, that has to be slave. So again, I'll swap master and slave surfaces and just hit OK. So now I'm all set. As you see in the last step, actually there are 2 contact pairs, and the simulation goes all the way through until the clip is fully inserted. Okay, again, I don't want to run it because it takes about 20-25 minutes, which we don't have, and I'll do the same as before, which is I'll simply attach the solved results. I'll create a new analysis, and I'll import a database for analysis. Okay, let's take a look at a couple things. So as you see, the clip is now fully inserted. Let me run an animation. Okay, so that's the first step. Then it rubs against the smooth surface. It goes in. You can see what's going on. Okay. Then it goes through, and you see the contact is now occurring at the very top. And it goes back because the simulation is, the animation goes back and forth. Okay. And I'll close it. So I'll take a look at another thing, which is what I want to see is the amount of plastic strain once the clip is fully inserted. So that is the static step 3. Right-click, generate result image, and I want to look at the equivalent plastic strain. Hit OK. Yeah. So essentially, you see there is a little bit of plastic strain still remaining in the clip once it's fully inserted. And lastly, I want to see the insertion force, how it changes through the deformation and through the insertion, which is, that would be history request, reaction force. And I want to plot for all steps. You see there's static step 1, 2, and 3. So as expected, as you see, initially the insertion force was increasing. Then, once the clip starts rubbing against the smooth surface of the inside, actually it starts decreasing. And at some point, actually the clip was going in all by itself without any insertion force. The insertion force is actually negative. It actually makes sense because once the clip achieves configuration when it's kind of, this surface starts rubbing, actually, let me close it. So what I want to do is bring back the deformed shape and remove this one. Okay. And I'll run an animation and I'll explain what I mean. So okay, let's wait a bit more. So once it reaches this configuration, the clip goes in all by itself. Okay, and so that's why the reaction force is actually changes sign, but then it starts increasing again. Why it starts increasing again? Because the cap starts pressing against the panel. So all the results, as you see, make perfect physical sense, and we accomplished our task. I'll close it up. And that's pretty much all my demo. As a summary, let me go back and revisit a couple of key points. Okay, so just to summarize what we've seen here, what is ANL? ANL stands for Abacus Nonlinear Analysis. It's a CATIA V5 technology, and essentially it's the Abacus technology built into CATIA. What is specific about it? First of all, it enables nonlinear static simulation, including material nonlinearity, geometric nonlinearity, and also sliding contact with friction. It is fast and accurate because it uses the industry-leading Abacus nonlinear solver, and on the upside, it is very easy to use. The target users are not CAE analysts, are not dedicated analysts, these are CATIA engineers and designers. So that kind of concludes my presentation, and I think now the host will chime in, and we'll start our question and answer period. Kareem?
Wonderful. Yes, thanks very much. Just want to let everyone know as well and remind you, this webcast is brought to you from by RAND 3D, which is a division of RAND Worldwide. RAND 3D offers training, software, and consulting services for users of Dassault Systèmes software. As well, they also provide training classes for PTC software products.